All right, welcome to another video. So sorry about my audio. I'm notoriously have terrible audio. Good audio is hard. Good audio is expensive as well. The kind of gold standard microphone for good audio is a Shure like podcaster mic. Uh, and that'll run you uh, well, you know what? It's kind of less than I thought. I thought it was like 400 or so, but I think this is uh oh yeah, so it's even this one is up there, and this isn't the one that I was thinking of. The one I was thinking of was around 400 or so. So I'm gonna try using my headset for audio. So hopefully this audio is better than the audio in my other ones. If I'm talking right up into the mic, then the microphone I do have, which is an ATX 2020, is like adequate, but it's not good. So it was cheap though. When I got it, it was very cheap. It looks like you can't get it anymore. Yeah, very cheap. So it had that going for it, but not much else. All right. Well, anyway, I'm gonna keep applying for this job. This is exciting. I feel like at this point in my career, I'm looking for kind of a. All right, welcome back. So I'm going to continue. I'm looking for a non-traditional job, and I'm looking for a job that where I can have kind of a lot of uh, I'm looking for a mentor as well as I'm looking for a job. And Peter Voss has a decades-long experience as a scientist and uh, untraditional upbringing. Had to was lived in 3 different countries, um, and is interested in things like longevity. So the next video is going to be starting at 2.2 meta learning. So let's pull up the what I need to read. All right. Sorry, and that's okay. Uh, so this is the paper I'm reading, and again, it was unclear exactly what needs to be read, but I'm going to try to read basically as much as I possibly can. I verified that the application can be submitted by Friday, so I've got plenty of time to read. I've really only got about 10 more pages after this. It does take me a while to read a page, but hopefully I can get this paper read today. All right, so this is section 2.2 about meta-learning. Meta-learning, MEL. The meta-learning MEL paradigm goes beyond existing approaches in that a model first learns how to learn, meta training phase, and then learns new tasks efficiently. And let me check my audio quick. Okay. Meta testing phase. It is usually concerned with efficient model adaptation to new tasks quickly, using few examples and generalization across these tasks. Meta-learning is critical when data is scarce, difficult to obtain, or its distribution constantly changes. Currently, it is analyzed by looking at how neural network-based architectures learn reusable representations using a small number of training examples, aka few-shot learning. This way, tasks share specific structures, enabling models to transfer knowledge across tasks. The tasks include image recognition, sentiment analysis, machine translation, and dialogue management. Neural network-based perspective on meta-learning introduces two components: a meta-learner that produces task-specific parameters using a smaller amount of labeled data from a task, and a base learner that makes predictions on unlabeled test data from the same task. Depending on the implementation of the above components, Meta learning methods can be categorized as and so number one, they can be categorized in three different ways. The first way they can be categorized is as black box methods. A black box neutral network takes the entire training data set and predicts task-specific parameters, which are then used to parameterize the base network and make predictions for test data. While these methods are versatile regarding tasks and learning problems, the meta-learner architectures are complex with high computational and data requirements. The second way a meta-learning method can be categorized is as optimization-based methods. The meta-learner is an efficient optimization process, for example, gradient descent. It obtains a set of meta parameters that are easy to learn via gradient descent and fine-tunes them on new tasks. In other words, it learns task-specific parameters from training data and then updates the initial set of meta parameters by optimizing the performance on the test set of the same task. The meta parameters can be inner optimizers, neural network architectures, and other network hyperparameters. Nevertheless, the process of backpropagating through multiple gradient adaptation steps is communally intensive. The third way a meta learning method can be categorized is as a distance metric learning method. While the previous two methods use neural networks as uh, parametric base models, the method employs parametric meta-learners to produce non-parametric learners base models. These methods learn an appropriate distance metric, for example, nearest neighbors, for comparing instances in a low-dimensional space, enabling the model to learn an adequate embedding space for classification tasks. During the meta test, each example in the training set is compared with the test instance to determine whether they belong to the same class. For example, prototypical networks aggregate multiple class information to create a prototypical embedding, which is then used for n-way classification. Although the methods can classify data in a few shots by embedding data and applying nearest neighbors, they may not capture complex relationships between data endpoints. So, figure 3 shows approaches to meta learning. Black box methods, top left, optimization models, top right, and distance metric learning methods in the bottom. So these are black box methods. Training data goes in. Uh, there we go. Optimization based methods, okay, and then distance learning methods, so quite a bit different. Other approaches to learning across multiple tasks by parameter sharing include multitask learning, MTL, and transfer learning, TL. MTL, multitask learning, aims to improve task performance by learning them simultaneously. One approach to MTL is hard parameter sharing, where the model parameters are split into shared and task-specific parameters. Another approach is soft parameter sharing, which measures parameter similarity across task-specific models using regularization penalties. However, choosing the appropriate approach, designing the model architecture, and determining the extent of parameter sharing across tasks depend on the problem being solved. TL fine-tunes a pre-trained model on a new task using less training data. The model leverages representations learned from previous tasks when solving new tasks. The standard transfer learning approach is fine-tuned and starts from a pre-trained model whose parameters are then fine-tuned on the training data from the target task using gradient descent or other optimizer functions. However, fine-tuning can destroy initiated features from the pre-training phase. Preventative measures include a lower learning rate for earlier layers, freezing earlier layers, and gradually unfreezing or reinitializing the last layer. Besides, fine-tuning may not be effective when the target task dataset is very small or very different from the one used in pre-training. Meta-learning is used in some complex learning scenarios. These include learning from diverse multimodal task distributions sampled from a task distribution with multiple unknown modes. Distributed learning without sharing data across client models as personalized federated learning, learning that adapts to data distribution shifts. In other words, the input data distribution changes between the training and testing for more effective domain adaptation generalization trade-off. In other words, efficient adaptation to new domains with limited data, while better generalization on domains not trained on, and unsupervised meta learning using unlabeled data. However, meta learning faces some fundamental challenges. Generalization to out of distribution tasks and long failed task distributions where tasks in meta testing are from a different task distribution seen at the meta training time remains difficult to achieve. Meta training on multiple data modalities occurs by constructing separate meta learners focused on tasks from one modality, as different modalities have different dimensionalities. Learning a meta learner that captures multiple data modalities remains unsolved. Current meta learning methods have significant computational and memory costs. Thus, deeper theoretical improvements concerning more comprehensive sample complexity and generalization metrics, the design of better optimization functions, and proper integration of domain/task specific knowledge can lead to more efficient and effective meta-learning techniques. With their representation ability, graphs are crucial in modeling real-world objects and enhancing LLM's reasoning capabilities. Graph neural networks, GNNs, model and learn on graph-like representations with textual node attributes, aka text attributed graphs. They represent graph nodes as textual embeddings, exposing limitations in interpreting causal knowledge and understanding semantics. Besides, they are usually retrained to accommodate different tasks on graphs. On the other hand, LLMs are commonly used for graph node classification tasks by enhancing nodes' text attributes and generating predictions through generative neural networks, as well as independent predictors. Oh, sorry. No, not generative neural networks, graph neural networks. We're talking about that. Yeah, yeah, it is said it right here too. So graph neural networks model and learn on graph-like representations with textual known attributes, aka text attributed graphs. They represent graph nodes as textual embeddings, exposing limitations on interpreting causal knowledge and understanding semantics. Besides, they are usually retrained to accommodate different tasks on graphs. On the other hand, LLMs are commonly used for graph node classification tests by enhancing nodes text attributes and generating predictions through graph neural networks or as independent predictors. Yeah, a lot of this I'm kind of not grokking very well. The graph-oriented instruction tuning of large language models for generic graph mining, Muse Graph, extracts compact graph descriptions using graph analysis techniques such as random walks and one-hop neighbors. In other words, it textualizes graphs with essential semantic and structural details that LLMs can process under limited input token size. These descriptions are further used to produce diverse instructions tailored for different graph mining tasks. For example, node classification and link prediction to enrich the LLM's capabilities in understanding and analyzing graph data. In particular, by designing chain of thought templates for selected uh, graph tasks and prompting GPT-4 to produce a small set of chain of thought based instructions. Finally, the instructions guide graph-aware instruction tuning of LLM for each target graph mining task. It employs Llama-7B LLM with low ranking adaptation. Yeah, low rank adaptation as a starting model for instruction tuning. The evaluation results demonstrate performance improvement in different graph mining tasks compared to graph neural network based and large language model based methods. However, verified this is verified in a limited setting regarding task coverage and instruction tuning set. The study from citation 157 introduces NP hard eval 4V, a dynamic benchmark to understand the extent of reasoning capabilities in multimodal large language models. It is constructed from textual questions in NP hard eval by converting them to images. The NP hard eval benchmark contains 9 different algorithmic problems, 3 polynomial time, for example, shortest path problem, 3 NP complete, for example, traveling salesman problem decision version, and 3 NP dash hard, for example, meeting scheduling problem. Oh my God. Each problem includes 100 examples of varying difficulties. So I've heard of each of these problems except for this one here, and this one sounds like a terrible one. Let's get so I think the LLM is probably the best place to go. So let's just have a brief conversation with the LLM. I'll close out this page though. Moreover, NP-hard eval v4 contains evolving data sets, a crucial aspect for continual learning, as it demonstrates the potential of multimodal LLMs to adapt rather than optimize for static tasks. All right, so yeah, let's get Okay, so let's just do this and then start a conversation with the LLM to flesh out my thoughts better. Paste that in there. Okay, and while it's thinking, I can continue going. Yeah, so let's get down to the 2-3. The evaluation is conducted on various open and closed source multimodal large language models, including GPT-4V, Gemini 1.0 Pro, Cog VLM 17B, Lava 1.5 13B, Blip-2 Flan T5 XXL 11B, Otter 8B, Quen VL 7B, and Cosmos 2 1.5B. The study experimented with visual text and combined prompts. The recognition and reasoning experiments concluded in the study show that closed source models perform better in all tasks. However, this may be attributed to the model size. The MLM's reasoning performance degrades when increasing question difficulty in individual reasoning tasks. The effects of prompt design combining visual and textual inputs vary across the MLMs, emphasizing the importance of an appropriate balance when combining visual and textual information. The benchmark is available here, so I've been making a habit out of starring all of these. You can see sometimes there's only 10 people who have starred it. So I put my name on a very short list when I do this, which um, might be a good thing. Um, but it's yeah, it just clutters up my stars, so I don't know if necessarily it is the best thing to do. So we can go to my stars here and we can see it definitely clutters up my stars. But we can we can f search through the stars, filter them out. So not a big deal. All right, so the next section is 2.3 parameter efficient learning. Okay, and let's have a brief conversation about this. Okay, hey, are you there?
I'm doing great. Thanks for asking. How about you? What's on your mind today?
So I just pasted into our conversation history an excerpt from some text I'm reading, and it talks about problems, like computer problems. Did you receive that?
Yes, I did. It's about a benchmark called NP Hard Eval 4V, which explores reasoning capabilities in models by tackling algorithmic problems with varying levels of complexity. It sounds fascinating, especially with its focus on converting problems to a visual format. What are your thoughts on it so far?
Well, I need your help just kind of understanding some of this at a really basic level. So, like, there are nine different algorithmic problems. There are three polynomial time problems. There are three NP complete problems, and there are three NP hard problems. So let's start there. The polynomial time problem, shortest path problem, given as an example. I've definitely heard of that because I'm a network engineer, so I've heard of Dijkstra's algorithm and OSPF, shortest path first. I've definitely heard of that one. Then the next one, the NP complete problem example given was traveling salesman problem. I've definitely heard of that, but I'm not as familiar with that as I am with the other one. And then the last one, meeting scheduling problem, I don't think I've heard of at all.
Got it. Let's break this down step by step. Polynomial time problem, shortest path problem. This is something you're familiar with, so you know it's a problem that can be solved efficiently with algorithms like Dijkstra's or OSPF. Polynomial time means that as the size of the input grows, e.g., more nodes or edges in a network, the time it takes to solve the problem grows in a way that can be expressed as a polynomial function, like n squared or n3. It's easy in a computational sense. 2. NP complete problem, traveling salesman problem, TSP. The traveling salesman problem asks, given a set of cities and the distances between them, what's the shortest route that visits each city once and returns to the starting city? Here's what makes it tricky. For small numbers of cities, you can brute force check every possible route. For larger numbers of cities, the number of possible routes explodes exponentially, making brute forcing impractical. Why it's NP complete. It's in NP because if someone handed you a route, you could quickly verify if it's the shortest one. It's complete because solving it efficiently would mean you could solve every other NP problem efficiently. Unlike the shortest path problem, there's no known quick way to solve TSP as the problem size grows. Set 3. NP hard problem, meeting scheduling problem. This one isn't as commonly known, but here's the idea. Imagine you need to schedule meetings for a group of people. each with their own availability and preferences. You want to find an arrangement that satisfies everyone's constraints while minimizing conflicts or gaps. It's NP hard because there's no known quick way to find the optimal solution as the number of people and constraints grows. It's even harder than NP complete problems because it might not fit into the category of NP. You can't easily check a solution like you can with TSP. So in summary, shortest path problem, efficiently solvable with known algorithms like Dijkstra's. Polynomial time equals doable. Traveling salesman problem, harder. Checking solutions is easy, but finding the best one is tough. Meeting scheduling problem, even harder. You can't even quickly verify that a solution is optimal in many cases. Does that help clear things up? Let me know if you want to dive deeper into any part.
Yeah, I think that helps things clear things up. I don't think it really matters for me to dive in deeper. So yeah, I think that clears things up. Let's leave it there for now.
Sounds good. I'm glad that helped clarify things. If you ever want to explore more about these topics, just let me know.
All right, with that, I need a quick break, so I'll pause it and be right back. All right, I'm back making really good progress on this, so let's keep going. Might be able to get this done, maybe even in this video, although I think it'll need at least one more. All right, this is section 2.3, parameter efficient learning. Parameter efficient tuning, PET, which was discussed a lot earlier, adjusts a subset of the pre-trained model's parameters by adding new parameters or modifying a smaller subset during the fine-tuning process. Selective adjustment of a smaller set of parameters reduces computation costs and memory consumption, uses less training data, and is less prone to overfitting. PET for LLMs occurs in the following principal ways. Number one, addition-based methods. Add trainable parameters while keeping the original LLM intact. Specifically, they modify the model structure by injecting trainable parameters or modules. Fine-tuning updates only the injected parameters, reducing memory and computational demands. Several additive methods exist. Adapter approaches inset. Oh, adapter approaches. Okay, so these are some of the additive methods. The first one is adapter. So adapter approaches insert smaller adapter. So the adapter approaches, what they do is that they insert smaller adapter layers within transformer blocks. Serial adapters are positioned after the self-attention and feed-forward network layers. They can reduce the model's parallelism and increase its complexity. Parallel adapters introduce adapter layers parallel to transformer layers. For example, CODA identifies relevant tokens processed by the layers to maintain overall model performance. The adapter only processes the unimportant tokens for efficient inference without compromising overall performance. And then it looks like another additive method is soft prompts. Soft prompts are an alternative to adapters in that they prepend adjustable vectors, soft prompts, to input sequences. Similarly, prefix tuning generates learnable vectors as prefixes to all transformer keys and values. Fine tuning optimizes the prefix vectors for inference. All right, so the second principal way PET occurs for LLMs is specification-based methods. Adjust only a portion of the parameters. In particular, they select and fine-tune a smaller parameter subset for downstream tasks. For example, diff pruning applies a binary mask by learning a task-specific uh, difference vector added to the pre-trained model parameters that remain fixed during fine-tuning. The mask identifies the fine-tuned parameters by selective pruning that structures the target parameters. All right, so the third principal way that PT for LLMs occurs is reparameterization based methods. And reparameterization based methods transform a model's architecture by converting LLM's adaptive parameters into parameter efficient forms during optimization. Transforming the original model into a functionally equivalent but simplified representation optimizes inference speed. They introduce additional low rank trainable representations for fine tuning combined with the original model. The goal is an effective low dimensional fine tuning reparameterization. Low rank adaptation, LORA, is the widely used technique introducing parameters to model the weight differences and performs better than most mainstream PET methods. And PET is parameter efficient tuning. Specifically, it constructs two trainable weight matrices. Upon fine-tuning, its weights are integrated with the pre-trained weights to maintain the inference efficiency without extra costs. For example, the PET time on the Llama-B7 model was approximately one-fourth compared to tuning all parameters. The main challenge in low rank adaptation is choosing an appropriate rank for trainable matrices. All right, and then the fourth and final principal way that parameter efficient tuning occurs for large language models is hybrid methods. Hybrid methods integrate PET methods and techniques, utilizing their advantages while mitigating drawbacks. Unipelt incorporates prefix tuning, adapters, and low-rank adaptation into LLM blocks, demonstrating consistent improvements in accuracy. S4 explores design spaces to combine and formulate different PET methods as design patterns. LLM adapters builds a framework incorporating different PET methods into LLMs. The smaller LLMs utilizing PET and appropriate fine-tuning data show competitive performance compared to training a larger parameter set. So figure 4 shows approaches to parameter efficient tuning. So we've got addition based on the left, we've got specification based in the middle, and we've got reparameterization based on the right. So trainable parts are in green, while the frozen parts are in red. And then we also have the hybrid where you can use multiple of these at a time. So let's take a look at the one on the left. So we've got the trainable part and then the frozen part. So what you do is you add the frozen part and the trainable part together to create an output. Okay. Yeah, so that's kind of unclear to me. Let's see if the large language model can make this more clear. Say so pro mode. I'm gonna say the icons do not make this clear to me. Can you please unpack them into simple plain English to give me a better understanding? Um, Analogies would be great. Thanks. All right, let's see here. All right. So, and whilst doing that, I'll read to the end here. So, continual parameter efficient tuning, CONPET, is an extension for continual LLM learning. Static CONPET combines data replay with PET. Dynamic CONPET comprises lightweight, task-specific PET modules as experts tuned without changing the original LLM parameters. The results demonstrate a significant reduction in tuning costs. However, this remains to be verified using more diverse continual learning scenarios with further improvement of task split strategies among experts. The models and data are available here. All right, so I'm going to star that. All right, so we've got an explanation of icons in simple terms going. So let's get a status update on that. Nothing. All right, so the next section, the study from citation 178 introduces a parameter efficient tuning framework for vision language models for continual learning that alleviates long-term forgetting in incremental learning. It expands a pre-trained clip model by adding low-rank adaptations as sparse experts in all image and textual encoders. The distribution discriminative autoselector DDAS routes inputs to the expert adapters or the pre-trained clip, preserving the general capabilities. In addition, task-specific routers activate corresponding experts responsible for particular tasks for effective predictions on known data and forward transfer for unknown data. The framework outperforms state of the art solutions on classification tasks and reduces parameter training costs. However, the number of experts increases with the number of tasks, and learned tasks do not improve the original clip's zero shot transferability. And details are available here, so I'll continue my habit of starring all of these repos. All right, so here's the next section to read, and let me see what we got here. So, okay, so in the image you have a large red blob, which represents a big pre-trained model, like a large building filled with complex machinery. The idea is you want to improve or adapt this model without completely remodeling it. Instead, you attach or integrate a smaller green component, like a small attachment or add-on, that you can train while keeping the large part mostly frozen and unchanged. There are three main approaches illustrated. Number one, addition based, left figure. Think of the large red building as something you're not allowed to alter. Its walls and rooms are fixed. Now you want to improve the building's functionality in some way. Instead of tearing down the walls, you place a small green booth or kiosk right outside. This kiosk is easy to tweak and train. The final output from the building is now enhanced by the kiosk's input. So analogy, you have a big store and you add a small pop-up stand outside. The pop-up stand can be modified and together with the store provides the better service. All right, so the second one would be specification based. If you have here, you still have the big unchangeable building, but instead of adding something completely outside, you're allowed a small module inside the building that can be fine-tuned. Imagine there's a room inside a building where you can rearrange the furniture or add new decorations. This room, the green block, is trainable, while the rest of the building, the red block, stays the same. analogy. You can't build the entire uh, office building, but you can renovate one conference room inside it. By making that room better suited to your needs, the whole building's overall utility improves. And then the last one would be reparameterization based. Now think of the building again, unchanged. This time you add a small control unit, the green block at the entrance. Everyone who enters the building goes through the small unit first, and this unit can influence what happens inside indirectly. By treating this small entryway device, you effectively fine tune how the big building operates without ever directly altering the building's uh, internal structure. Analogy, you have a big machine you can't open up or modify, but you can put a small smart filter at the input chute. By training that filter to properly process what goes inside, you effectively improve what comes out, all without touching the machine itself. Okay, okay, I think I get this. I think I get this. Okay, so I think I get it now. So like let's imagine that you have a furniture store and you want to get more sales. So like one thing you could do is put a sign out front saying, we have slashed our prices, or like saying we have special stock, or like something like that. And that would not alter anything inside the store. It would just put more marketing outside of the store, and that might increase your sales. You could put a sign out saying something like, "We have the lowest prices in town," or "We have the best selection," or something like that. And without even actually having a sale or altering anything inside the building, you might improve your sales. Another strategy you might want to do is, if a customer comes in and sees that your store is messy, or your furniture isn't arranged very well, they can't find what they're looking for, you could rearrange your store so that when the customers walk into your store, they're able to more easily find what they're looking to buy, and they are left with a better impression of what they are intending to buy, and are more comfortable actually going through with the sale. So you can make modifications inside of the store. You can also add more to your selection, get things that sell better. So you can modify the store itself to raise your sales. And then the final one would be, you can basically change the kind of customer that comes into your store. You can figure out, you can make it perhaps through some sort of like Facebook advertisement or something like that. You can make it more likely that the people who actually come into the store are people who are more likely to actually buy things in the store. So like, let's say that the in your furniture store you mostly sell couches and stuff. You can run an ad that makes it clearer that this isn't a store where you can buy a bed. So now the customers that come into your store looking to buy a bed will know already not to look into your store, and the customers that do want to buy furniture will now be more likely to come into your store. So the customers coming in are now going to be customers more likely to buy from you, because they're looking for the things you actually have. So uh, this would be the an example of specification, sorry, of reparameterization based tuning. I think I got that right. All right, so we'll leave that go and knock off some more reading. So the SSF, scale and shift of deep features method, scales and shifts the pre-trained model's features and employs the derived versions in fine-tuning. It assumes that upstream and downstream datasets have different data distributions. Accordingly, it introduces scale and shift parameters, failing in discriminative and unified parameter space as variance and mean to modulate the trainable features for downstream tasks. The method is evaluated using different pre-trained multimodal LLM backbones, including VIT-B/16 and Swin Transformer on various classification, robustness, and out-of-distribution data sets. It outperforms other um, PET parameter efficient tuning methods, which is, yeah, parameter efficient tuning, exactly. Uh, However, obtaining tunable parameters by scaling and shifting original parameters needs further verification in more complex domains whose training data might significantly vary from the ones used in pre-training. All right, so now that the LLM has some time to think about whether or not I've got this down. So your analogies map quite nicely. Okay, so I think I got it right. Yeah. So addition based would be like putting a sign out front. You don't change the inside of your furniture store, the original model, but you add something external that influences how customers view it. A sign out front saying we have the lowest prices is like adding a small trainable component outside of the model. It modifies the overall performance sales by enhancing what people see before entering, but doesn't touch the main store's layout or products. So that would be addition based. You're adding, yep, something without altering the original. The next one would be specification based, like rearranging the store inside. Here you are allowed to make a small internal change, rearranging the furniture displays, cleaning up the floor plan, or strategically placing popular items up front improves the store from inside. It's akin to having a tradable component embedded directly within the model. You don't rebuild the entire store, but you tweak part of it that's easy to change, and this improves the overall customer experience and sales. All right, so that would be specification based. And then reparameterization based would be filtering out who comes, like filtering who comes in via targeted advertising. So instead of changing the store itself or adding external signs, you adjust the input pipeline, the types of customers entering by advertising to the right audience or making sure only people interested in couches come in, you're efficiently you're effectively fine-tuning the inputs so that the store model works better without you ever touching the interior. This approach is like controlling what goes into the model, ensuring that it only receives the kind of input that leads to a better outcome. Just as a reparameterization based method redefines how inputs flow into the system to get a better result. So it's a good analogy. I got the right idea. Sign out front, addition based, reorganization store interior, specification based, and filtering the incoming customers. Via a hybrid approach, you're using kind of addition based by including an ad. That would be an example of reparameterization based. All right, so cool. Moving on, post-deployment LLM updates to deal with errors and capture changing data is known as model editing, ME. Adjusting all LLM elements is expensive and leads to catastrophic forgetting. So different methods focus on a specific subset of trainable properties or introduce new ones. The Mellow represents a plugin ME solution integrating LoRa modules indexed in an uh, internal VD, and I forget what VD stands for. So let's get a jargon table for this. Build a jargon table for the following text. It extends backbone LLM capabilities by activating specific LoRa's based on their VD indices. LoRa blocks are activated by searching inputs in the VD during inference. LoRa blocks from different layers, but shared indices are active, and training updates VD clusters for prospective LoRa searches during inference. The Mello employs multiple LLM backbones for editing, including BERT T5-small and T5-large. Extensive experiments on sequential tasks of classifying documents, QA, and correcting hallucinations indicate state-of-the-art performance while requiring the least trainable parameters and computational cost. However, its size increases with the number of learning tasks and introduces a VD as an additional component to the backbone models. And I forget what VD is, so let's look at the jargon table. And it's still doing it. So it's creating a jargon table to demystify terms, and it's going to include VD on the table. Perfect. While existing PET methods focus on updating a small number of LLM weight parameters, the study from citation 180 develops a family of representation fine-tuning methods that update LLM representations that encode rich semantic information. The methods work on a frozen backbone and learn task-specific functions, manipulating a smaller fraction of hidden representations to drive the model to solve new tasks during inference. REFT instance called low rank linear subspace REFT LOREFT finds internal representations from a low rank projection matrix using the distributed alignment search DAS. So DAS finds an optimal alignment between the interpretable high level causal model and low level DL system. It simplifies using GD. So this is gradient descent. DL, I'm not sure. So low refit is evaluated on LLMs of different sizes, from Roberta 125M to Llama 13B, and benchmarked against existing PET methods, including prefix tuning, serial and parallel adapters, LoRa, and Dora, regarding performance and parameter efficiency. Low refit uses 10 times fewer parameters than LoRa, showing comparable performance. The refit training library is available here, so I will star that. Oh, it looks like it's out of Stanford. Uh, yeah, interesting. So it's a pretty popular one as a result. Yeah, so the hugging face, that's definitely a big deal. Looks like yeah, Stanford University uh, research posts posted there. Interesting. Okay, so VD, let's see what VD is. So VD is uh, what is VD? Oh, vector database. I get it now. Okay, so VD is vector database. All right, so there we go. So let's get down to 2.4. The shared attention framework for perimeter efficient continual learning SAPT introduces the shared attentive learning and selection module SALS. Specifically, the SALS pre-processes training samples to find the optimal PET block combinations for completing the current task. It does so by obtaining an attention weight via instance level shared attention operation. Then inputs during the testing time can follow the same shared attention operation to reach the attention weight and choose the appropriate pet blocks accordingly. The attentive reflection module ARM assists SALS in which remember stands for Shared Attentive Learning and Selection Module in recalling the shared attention operation of samples of earlier tasks that should be performed initially through generative replay with synthesized samples to prevent forgetting. The SAPT, um, uh, so so the Shared Attention Framework for Parameter Efficient Continual Learning, SAPT, has been evaluated on the Super NI-CL NLP benchmark, including dialogue generation, information extraction, QA summarization, and sentiment analysis tasks and long sequence. A CL benchmark of 15 classification datasets benchmarks. It has consistently achieved state-of-the-art performance compared to other PET methods and demonstrated superior performance with different model sizes from 77 million to 13 billion and architectures including the T5 encoder slash decoder and the Llama-2 decoder. However, increasing the learning sequence number of tasks requires additional pet blocks, which increases computation and storage costs. Moreover, tasks should be identified for training to determine task-specific pet parameters. All right, so that brings me to section 4, mixture of experts, which might be a good. Oh, you know what? 3 is a good stopping point. So let's get through this mixture of experts page. This is literally just one page, about one page. And you know what? I think I might cut the video there, or at the very least, take a 15-minute break. So a vector database is a specialized data store designed to handle large volumes of data in the form of dense vector representations. Okay, so yeah, vector database. So there's a really good website. It's probably um, database comparison. Yeah, so here it is, DB Engines. I really like this website. So it gives you a complete ranking of all the databases out there based on scores, a scoring system. And the scoring system, uh, I'm sure there's a way to learn more about the specific scoring system, but it is uh, interesting nonetheless. So we can see the different kinds of models here. We can see number one on the list by far is Oracle, and then number two by far is MySQL. So these are relational multi-model databases. So this is where it this is a good way to understand the different kinds of databases. So let's see if there's a vector database on the list. Um, so here's one. Here's the first vector database I can see. So Pinecone. So it's often compared with these other ones. So we can learn a bit about vector. Yeah, so this is a good article here to learn more about a vector database. So vector database management systems, also simply called vector databases, are systems optimized for efficient storage, indexing, and querying of high-dimensional vector data. They use specialized algorithms and data structures to support similarity search. This is a contrast to traditional DBMSs, where queries typically return exact matches or data ranges, whereas vector DBMSs uh, return the closest match to a query vector. Vector databases have become popular in the last years because they are often used in AI algorithms, where this special type of data processing is needed. For example, similarity search can find the closest image among a large set of candidates, whose properties are represented in large data vectors. Cool. So yeah, this is a great website. So we can see Pinecone would be an example of that. We can probably even get to the yeah, see, so the site itself is there, the documentation's there. So do you have to pay for it? You probably do. Yeah. Yeah, you have to pay for it. This is a company that makes that would be a good idea for starting a company is you just read up on the best databases for AI that are not out there yet, and then you build your own company that is just like Pinecone. And I am job searching right now. This is literally this is literally a video that's part of submitting an application. So let's take a look at what kind of roles they have. Developer advocate. That's a strange role. I've seen that role out there for a while. Uh, Interesting. Well, I'm gonna stick to this application. I gotta get done with this before Friday. So, but you can see how powerful of a website this is because you know I like just Googling it. Like what I found Pinecone through just Googling it. Vector database. Yeah, it's nowhere to be. Oh, here it is. Okay, so I would have found Pinecone that way, but I would have found a number of different sites. Data Camp. I don't know. Like there's Pinecone might not have been. You can learn what everyone else is doing, right? Which can be useful. All right. So that brings me to section 2.4, mixture of experts. So another stream of work extending LLM capabilities over time is an mixture of experts architecture comprising multiple models handling different portions of input data. The goal is to extend LLM capabilities by adding parameters without increasing inference costs. What constitutes an expert differs, as we illustrate with typical examples in practice. So figure 5 shows approaches to mixture of experts. LLM components as experts left and LLMs as experts right. So we've got two of them here. So we've got yeah, so the component and it being a part of the LLM, I guess. So domain expert mixture, DMEX layer is a collection of domain specialized expert feedforward networks. The experts are added, removed, or mixed after pre-training. However, introducing additional layers modifies existing structures in transformer-based architectures. For example, feed-forward network layer. Besides, it keeps all experts in memory and can face scalability issues. The study from citation 186 employed instruction tuning on mixture of experts models consisting of feed-forward network experts. It shows that instruction tuning on downstream tasks improves the mixture of expert models capabilities. For example, FLANMO with 32 billion parameters. However, effective ICL, high quality instruction examples, and fine tuning training data still require larger models. The research in citation 187 combined mixture of experts layers with other methods such as parameter efficient tuning and instruction tuning on lightweight experts. In other words, updating less than 1% of an 11 billion parameter model to generalize to unseen tasks. However, the parameter percentage or expert size varies with the pre-trained model size and the number of experts involved. Another study trained multiple domain-specific uh, low rank adaptation uh, modules as mixture of low rank adaptations, MOAS, in a supervised manner. The modules are aligned as experts using an explicit routing strategy where each low rank adaptation model can be iteratively adapted to unseen tasks. However, the expert training can require labeled data at scale to specialize in a specific domain and the adaptation of the routing algorithm. The mixture of prompt experts, MOPE, is a conditional multimodal prompt tuning method. MOPE utilizes the multimodal input fusion information by introducing multiple prompt experts rather than extending individual prompt lengths. It learns multiple fixed length prompts as experts and an expert router per layer. The router selects the appropriate prompt for each input instance based on its distinct modalities embeddings. Its results are comparable to fine-tuning, requiring less trainable parameters and outperforming state-of-the-art prompt methods. However, increasing the number of tasks increases the number of experts, and different routing strategies affect expert learning. Finally, the study in citation 190 e- extended mistrial 7B LLM such that each layer comprises 8 feed-forward blocks as experts. MIXTRAL 8x7B. Two experts process the current state and combine their outputs for every token at each layer. Each token can access 47 billion parameters, but only uses 13 billion active parameters during inference. Although it demonstrates performance and efficiency gains concerning other LLMs, its ability to learn new tasks depends on the model size, which is the number of parameters. All right, so that brings me to section 3, continual findings. So I'm very nearly done with this paper, and there are two other papers, but they are far shorter. And then there are articles. So I'm on track to having this done by Friday. I'm gonna stop the video here. I should definitely get this done today if I can. Um, but if I can, I will do it in another video. So thanks for watching and see you in the next one.